Welcome to a lesson on mixtures involving first-order differential equations. In this video, we'll look at an example where the inflow and outflow rates are the same. So if we let A of t be the amount of the substance dissolved in a liquid in a tank at any time t, where liquid is entering and leaving the tank, the liquid entering the tank will contain a different concentration of the substance dissolved in the tank. So what we're saying is, we have a tank that contains a certain concentration of a solution. A different concentration is entering the tank, which instantly mixes with the current solution, and then the new solution is pumped out of the tank. So if this is the case, we can say that dA dt is equal to R sub 1 minus R sub 2, where dA dt is the rate at which A of t is changing in the tank, R sub 1 is the rate at which A of t is entering the tank, and R sub 2 is the rate at which A of t is leaving the tank. So let's take a look at our example. A large tank holds 200 gallons of brine solution with 40 pounds of salt. A concentration of 2 pounds per gallon is pumped in at a rate of 4 gallons per minute. The concentration leaving the tank is pumped out at a rate of 4 gallons per minute. The concentration leaving the tank is also pumped out at a rate of 4 gallons per minute. How much salt is in the tank after 1 hour, and how much salt is in the tank after a very long time? So using our differential equation, dA dt equals R sub 1 minus R sub 2. So we want to start this by finding R sub 1, the rate at which A of t is entering the tank, and R sub 2, the rate at which A of t is leaving the tank. To find these, we'll have to multiply the concentration times the rate. So for R sub 1, notice how there are 2 pounds per gallon, but it's being pumped in at 4 gallons per minute. So we need to find this product. So we have 2 pounds per gallon times 4 gallons per minute. Now the reason I'm writing this in fraction form is so that we can easily see that the units of gallons simplifies out. Therefore, R sub 1 is going to be 8 pounds per minute. Now R sub 2 is going to be a little bit trickier. We're going to have to write an expression for the concentration because it's changing as the mixing occurs. Notice how we start off with 40 pounds of salt per 200 gallons, but the 40 is changing, so we can't use that for our concentration. We have to use an expression, so we'll use A, where A is the unknown, divided by 200, and this would be pounds per gallon. And then the rate is the same as 4 gallons per minute. Again, notice how gallons simplifies out. So we're going to have, this would be 4A over 200, and this would be pounds per minute. But this does simplify. 4 over 200 is 1/50th, so we have A divided by 50 pounds per minute. So our differential equation would be dA dt equals 8 minus A divided by 50. Well, this is actually a linear first-order differential equation, which we can solve by using an integrating factor. Let's go ahead and set this up on the next slide. So just to review, if we have a linear first-order differential equation, then we're going to write the differential equation in standard form, or this form here, and then we're going to multiply everything by our integrating factor, which is given here. So you may want to pause the video here if you need this review. So I'm going to go ahead and rewrite this in standard form. So we'd have dA dt plus 1/50th A equals 8. So in this form, we should recognize that the integrating factor, mu of t, is going to be equal to e raised to the power of the integral of 1/50th dt. So this is just going to be e to the t divided by 50th power. And now we're going to multiply everything in this differential equation here by this integrating factor. So we're going to have e to the t divided by 50 dA dt plus 1/50th e to the t divided by 50 times a equals 8 times e to the t divided by 50th power. Now once we multiply everything by the integrating factor, remember the left side of this equation, or this side here, is equal to the derivative of the product of the integrating factor and our function a. So the derivative with respect to t, to the integrating factor, which is e to the t divided by 50, times our function a. So if the left side is equal to the derivative, then it must also equal the right side. So we'll set this equal to 8 e to the t divided by 50th power. And now we'll integrate both sides of the equation with respect to t. On the left side, the derivative and integral undo each other, so we're left with the exponential times a must equal, over here we have to integrate using u substitution. So notice here if we let u equal t divided by 50, then du is equal to 1/50th dt, so that means 50 du is equal to dt. So when performing the substitution, we're going to have an extra factor of 50. So the antiderivative will be 8 times 50 times e to the u, or e to the t divided by 50 power. And then of course plus our constant of integration. Okay, now our goal is to solve this for a, or a of t. So now we'll divide both sides by our exponential. So on the left side, simplifies to a, or a of t. On the right side, these exponentials simplify to 1, so we have 400. Then here, we can just write this as plus c times e to the negative t divided by 50th power. Now that we have the general solution, we can find the particular solution using the initial condition that a of 0 is equal to 40, because there's 40 pounds of salt to begin with in the 200 gallons. Let's go ahead and do this on the next slide. Okay, so if a of 0 equals 40, we'll replace t with 0. We would have 400 plus c times e to the 0, which is equal to 1. So this is just c. This must equal 40. So we'll subtract 400 on both sides. So c must equal, this would be negative 360. Therefore, the function that models the mixing solution is a of t equals 400 minus 360 times e to the power of negative t divided by 50. And now we can determine how much salt is in the tank after 1 hour, but we need to be careful here because t is time in minutes. Therefore, for 1 hour, we have to find a of 60, not a of 1. And we know this because the initial flow rates were given in gallons per minute. So our exponent here would be negative 60 divided by 50. And now we'll go to the calculator. So there's approximately 291.6 pounds of salt in the tank after 1 hour. And now for the last question, how much salt is in the tank after a very long time? We can answer this by finding the limit as t approaches infinity of a of t, which would be, again, 400 minus 360 times e to the negative t over 50 power. But I'm going to go ahead and make this a fraction, move this down to the denominator to help us find the limit. And we should recognize that as t approaches infinity, or gets larger and larger, so does this denominator, and therefore this approaches 0. Therefore the limit is equal to 400. This would be the amount of salt in the tank after a very long time. And hopefully this makes sense, because remember, we have 200 gallons in the tank. And since the inflow and outflow rates are the same, eventually the concentration would eventually be the same as the inflow concentration, which was 2 pounds per gallon. Again, gallon simplifies out, leaving us with 400 pounds of salt after a very long time. Okay, I hope you found this helpful.